let's solve this bonus quiz. It was very simple, but it just gives us a chance to repeat the last thing we did in the previous lecture. That was to solve an RC circuit. So I'll go over the solution again. So here is our situation. We have this capacitor C that is tied to a resistor over a switch. And initially, let's say I have a charge Q0. And here's my resistor R. Now, what do I expect when I close the switch? The positive charges on the upper plate would migrate over the resistor and neutralize the negative charges, right? So when I wait for a very, very long time, I expect all the charge to be neutralized, the total charge on the capacitor to go to 0. But we don't want just the final state. We actually wonder, after I close this switch at time t equals to 0, we would like to find out what's the current on the resistor. All right? So what's I of t? What is the charge on the capacitor as a function of time? And I also would like to find out the total power dissipated on the resistor. Right. How do I do this? And it's actually quite simple. Here is my circuit sometime after the switch is closed. Right. Now the charge here on the capacitor is no longer Q0, but it's some function Q of t. And the current is I of t. Now, what is the potential difference between the upper and lower conductors? Let's call this potential difference V. I can calculate it two ways. I can say V is either Q of t divided by C. That's one definition. I'm looking at the capacitor, right? Or I can say, okay, but this must also equal I times R. And I is also a function. So I can write 1 over RC Q of t is I of t. I very subtly used Kirchhoff's loop rule, if you want. Okay. If I go around the loop, total voltage change must be 0. Okay. Now, what's the relation between current and charge? Current was defined as the time rate of change of charge, right? dq dt. But let's be very careful here. Here I have plus charges. If I have a positive current leaving the plus terminal, does the charge increase or decrease? Now, the charges are going away from the capacitor, right? Positive charges are going away from the capacitor. So dq dt must be minus I. Okay? This is just the definition of current. Where are these charges coming from? Where is the charges that are carried as current are coming originally from the capacitor. So the current on my wire must equal dq dt in absolute value. And because it's leaving the plus terminal, I put a minus sign in front. Okay? Okay? Now I'm going to replace I here with this. 1 over RC Q of t is d by dt Q of t. As I said the last time, this is a differential equation, but it's really the simplest possible differential equation. It just tells me to find a function which does not change upon taking derivatives. And we know such a function. It's the exponential function. Furthermore, in 1 or 2 years' time, you will take a proper class on differential equations, which will tell you that if you find a solution to a differential equation, it's going to be unique. So if I find one solution, I'll be quite sure that it's the only solution. Some terms and conditions apply. I'm not going into details, but that's pretty much it. So we're going to solve this differential equation by inspection. Another way would be to do this. Let me take an aside. You can maybe write this as follows: dq dt. Then you'll do something which will make all the professors in the math department cringe. They'll go, oh, so let's do it. I'm going to move this dt to the left. And q to the right. So don't show this to your math professor, okay? That's obviously not a very good idea, okay? In general, you don't play with differential as if they are numbers. Nonetheless, if I integrate both sides, what would I find? I would find, let's say, from 0 to some time capital T, from q initial to q final, I would find the following: 1 over RC times T is integral dq over q is ln q, so it's going to be ln q final over q initial. And I missed my minus sign, I think, which is important. Or I can say q final is q initial times e to minus time over RC. That's one other way to solve it. Again, as I said, I have to be very careful writing these down. Do not let your math professor see what we did here. Okay? Nonetheless, I could also solve this by inspection. Okay? You have a question? Are you sure? No, you have a question. So.
I think we can do this. It's not a problem in differential equations.
Okay. Yes. That's a good comment. Feel free to say things like that. Now, my solution here is going to be an exponential. So dq dt is going to be alpha times e to alpha t. Now, I'm just replacing these into my differential equation, is minus alpha e to alpha t. So alpha is minus 1 over RC. So I find q of t as a e to minus t over RC. How do I find a? At t equals 0, I have a boundary condition. At t equals 0, q of t equals 0 must be q0, my initial charge. So a times e to minus 0 over RC must be q0. This is 1. A is equal to q0. So now I have found q of t as q0 e to minus t over RC. Let me plot this. Now, the first thing we should notice is that the scale on the plot is fixed by this combination. Tau, I'll call it RC. It's kind of interesting. When you multiply ohm by farad, you find seconds. And this is actually called the time constant of the circuit. So what happens if I wait for one time constant. Let's say initially when t is equal to 0, I am at q0. What happens when t is equal to RC? Q of t equals tau is q0 e to minus 1, right, at that point. So it's sort of 1/3 of the e is 2.7, right, 2.718. So it already went into 1/3 of its initial value, the charge. If I wait for 2 RC, Q of t equals 2 tau will be q0 into minus 2. So it's almost going to be 1/9 of its original value. So this will be pretty steep decline. The exponential function declines very fast. But most students, when they are faced with this exponential decrease for the first time, they say, hey, it keeps decreasing, but it's really never 0. So a capacitor never discharges. I'm going to counter that. I'll say, hey, the first thing we learned in this course is that charge is quantized, right? So what's the minimum possible charge? A single electron charge. So the question asks, if I start with 1 coulomb of charge, how long would it take for the charge to decrease to 1.6 10 to minus 19 coulombs? So the only thing I actually have to use is Q of t is q0 e to minus t over RC. What is the charge I'm looking for? 1.6 10 to minus 19 coulombs. Q0 is 1 coulomb. E to minus t. R is 1 ohm. Capacitance is 1 farad, so this is 1 second. So what's t then? T is minus ln 1.6 10 to minus 19 seconds. Let's calculate what that is. So minus, so in this program log means ln 1.6 10 to minus 19. 43.2. What's the unit? Seconds. So apparently if I wait for just 45 seconds, all the charge, even the last electron, would leave my capacitor. Okay? So, what sets this scale? Why do we call RC the time constant? If instead of a 1 ohm resistor, if I used a 1 kilo ohm resistor, would I have to wait longer time or shorter time? If that was a 1 kilo ohm resistor, then my time constant would be 1000 seconds, which means I would have to wait for 1000 times more. Okay, that's why RC is called the time constant. It tells you how fast this capacitor will discharge over the circuit. Okay, it's actually quite interesting. This simple circuit, RC circuit, is the simplest timer you can actually build. And it was used before everything went digital. It was used in a lot of circuitry. For example, your windshield wipers. there is this mode where they will wipe once and then wait for 2 seconds, wipe again. And how they accomplish that is they actually put a RC circuit in there. Every time it wipes, it loads up the charge to a certain level. When it falls below a certain level, it will wipe again. Okay. So any kind of timer was built in the analog days on this simple RC circuit. Now we have much better methods of keeping time, but still, RC circuit is important. Oops. Let me solve one more example. Let's charging a capacitor. So let's do the reverse. Now, if I have a battery of V volts, and I'm actually going to do the following. And let's say this capacitor is initially uncharged. What I'll do is I'll close the switch at time t equals to 0, and I'm wondering how the capacitor charges up. Okay, I would like to find the capacitor's charge as a function of time. Quick question. What will be the final charge on the capacitor? When will current stop flowing in the circuit? Come again? The potential should be the same, right? So here I have V volts. If I also get V volts across the capacitor, then there will be no reason for current to flow. So the final charge on the capacitor should be V, right? How do I find out this Q of t? I'll do the same thing. I'll actually, let's say, after I close the circuit, here is my situation. I have I of t here, which is entering the capacitor, and I have Q of t here. Now, I would like to use Kirchhoff's voltage law, and I would like to use it slowly so that we can do it. All of us can do it. I'm going to go along this loop and calculate the potential difference as I move along. In my first step, I'm going across the battery. What happens to the potential? Because it has V volts, I would say the potential has increased by V volts. So I have done the first section. The second element I see when I walk through this loop is a resistor with resistance R. What's the potential across the resistor? I times R. So V is going to be I times R. Is it decreasing or increasing as I go across the resistor? It's decreasing, right? The current is flowing down. The current is going from high potential to the lower potential. So I'll have I of t times R. What's the third element I see across as I walk along? It's the capacitor. What's the potential difference on it? It's Q over C. But is it positive or negative? Is it? I'm going from higher potential, the plus terminal, to the minus terminal. So it's going to be minus Q of T over C. And this all must give me, how about 0? That's Kirchhoff's law. Okay. So this is the equation I need to solve. Should I go through again? Maybe I should, yes. So let me go through again. I start from the lower conductor here. As I go across the capacitor, so if you want, let's sort of draw the potential. So I'm going across the circuit. I'll first pass through the battery. Draw this better. Then I'll pass through the resistor. And then I'll pass through the capacitor. And I'll actually come back to the same point here, right? Now, let's say the potential starts at 0 here. As I go from the minus terminal to the plus terminal of the battery, what happens? Potential jumps up. By which value? By whatever is written on the battery. Right? So it's going to go up by V. Then it will stay constant until I hit the resistor. Then what will it do? It will decrease. How much will it decrease? The change will be R times I. And then it's going to stay constant again. And then it will actually again decrease over the gap of the capacitor. And what will its final value be? It has to go to 0. That's what Kirchhoff says, because I went through a loop, I came back to the same point. Potential change must be, the sum of the potential changes must give me 0. And this distance is Q over C. That's my defining equation. So let's find out V minus I times R plus Q over C is 0. But again, what's the relation between the current and the charge on the capacitor? All this current is ending up as charge on the capacitor, right? And if I have positive current, I'm actually charging the capacitor. The current is entering the plus terminal of the capacitor. So I would say I of t here is going to be dq dt. So I can now write that. I can say V. By the way, you should warn me, I should be a minus sign. Minus R times dq dt minus 1 over C times Q of t is going to be 0. Now this looks like a little bit harder differential equation. But in effect it's not. I'll just do a change of variables. You see this? Okay, maybe first let me write it in another way. Let me write it as follows. dq of t dt is what? V over R minus 1 over RC Q of t. Right? So I'll do the following. I'll define a new variable. Define Q of t as Q minus, or even this, V over C minus Q of t. Can I do that? Why not? I'm just saying I'm subtracting Q of t from a constant. Now what's dq dt? D small q dt. V and C are constants. If I take a derivative of the constant, they are gone. Minus d q dt. So the same differential equation, maybe I can write as minus dq dt is 1 over r. I'm sorry, I did something terribly wrong. It should be v times c. Even the units do not match, right? V times c is q. So this is v times c. So dq dt is 1 over r c vc minus q of t. But that's exactly what I called small q. Or in other words, dq dt is minus 1 over rc q of t. Hey, do we know this differential equation? Yes, it's exactly the same differential equation we obtained for discharging of a capacitor. So it's not too different. It's not different at all. Okay. So what's the solution? Q of t must be whatever the value at 0 time is, e to minus t over rc. What's Q0 though? At initial time, capital Q at t0, the charge on the capacitor at t0 was 0. So Q0, which is going to be Vc minus Q at t equals to 0, is just going to be Vc. So I found the solution. Q of t is Vc e to minus t over Rc. Now I can go back. From here, I can say Q of t is Vc minus small q of t. So Q of t is going to be Vc minus Vc e to minus t over Rc, or Vc 1 minus e to t over Rc. So how do I charge the capacitor? It's very much like uncharging the capacitor, but now my charge starts from 0 and it has a limit which is going to be Vc, and the circuit approaches this limit exponentially again with some time constant Rc. So if t is equal to tau, I would have approached almost 2/3 of the way. If I wait for 2 time constants, I would approach, so this is going to be 1 minus 1 over e times Vc. This will be 1 minus 1 over e squared times Vc. So just as in my quiz question, if I wait for, let's say, 4 or 5 time constants, I would nearly fully charge my capacitor. Good. Let's solve one more example. Two ohms, 1 ohm. and capacitor is 1 farad. All the circuit is tied up to a potential source, a battery of 6 volts. And the question is, if we wait for very long time so that the system is in steady state, what is the charge on the capacitor? Any ideas? Now, does everyone understand the question? So I actually hooked up my capacitor to the circuit and I wait for a very, very long time so that the system is in steady state. What would you understand from steady state?
No current.
No?
No current.
Louder, please.
No current in circuit.
Well, not really, right? I mean, that would be, obviously there is a voltage source there. Okay. And that's okay. That's maybe if I wait so long that if I exhaust the battery, that would happen. But of course, that's not what I'm asking. No, I'm saying the currents are not changing with time. The voltages are not changing with time anymore. So dV by dt's and di by dt's are 0. So this is what you should understand from steady state. dV by dt goes to 0, di by dt goes to 0. Now, how is the current on the capacitor related to the voltage on the capacitor? Come on. Current on the capacitor is the derivative of the charge on the capacitor, which is C times dV capacitor dt. Right? So if I wait for a very long time in steady state, once the capacitor finished its charging or discharging, the current on the capacitor should be 0. So the question is actually quite simple. It tells me that, hey, draw the same circuit again. So I'm going to draw it again. Six volts, 2 ohm. Then I have 1 ohm. 2 ohms. 2 ohms. But here, instead of the capacitor, just put an open circuit. Think of it as if it's cut, because no current is flowing at the steady state. So if I wait for a long enough time, capacitors turn into just open circuits. All right? Good. Then can I find the voltage here? Of course I can. How do I do this? First, find total, well, can anyone tell me what's the result right away? What's the voltage there?
4.
4 volts, good. Who said that? Yes. Now, why is that so easy to find? We don't have to think about it. Let me quickly show you one thing. What would happen if I just killed the second 2 ohm resistor? Would anything change as far as the capacitor is concerned? No. Why? Because the potential between the two ends of the circuit is fixed by the 6 volt. Whatever current is going in there, I'm not concerned about at all. Okay. So I can do the following. I can very quickly say 6 volt from one end to the other. Whatever current is flowing here must also be flowing here, must equal I times 1 ohm plus I times 2 ohm. I used Kirchhoff's loop law in the outside loop of the circuit. Or in other words, 3 times I is 6, I is 2 amperes. So the voltage I'm looking for is I times 2, which is going to be 4 volts. Did the question ask the voltage? No, it asked what's the charge on the capacitor. And capacitance was 1 farad. So Q is equal to going to be CV, it's going to be 4 coulombs if I wait for a long time. I can see that many of you seem puzzled. That's entirely understandable. This is almost the first time you're facing differential equations, and this is almost again the first time you're actually facing capacitors in this time-dependent context. But I assure you, it's not hard. I mean, I haven't done anything that's beyond your mathematical skills. I took derivatives, and the only thing you need to remember is that exponential is a very useful function. When I take its derivative, I get back the same function times a constant. All right? Any questions? No? Okay, then I'll see you in the next lecture. Let me make an announcement again. Next week, I'll send an email, but next week I'm away. I'll not be here. Okay. I'll also talk to your recitation assistant. There'll be no recitation, so you don't have to come. Okay. So, but we are going to make up for all of these in the coming weeks. Okay.